Hello, everyone, and thanks, Professor Gopakumar, for the very nice introduction. For this session, we are very pleased to have with us Eric Mazumdar, who is an assistant professor in computing and mathematical sciences and economics at Caltech. Eric is the recipient of an NSF Career Award and was a fellow at the Simons Institute for Theoretical Computer Science for the semester on learning in games. He obtained his PhD in EECS at UC Berkeley, where he was advised by Michael Jordan and Shankar Sastry, and he received his BS in EECS at MIT. And over the next 2 days, he will talk to us about multi-agent reinforcement learning. Take it away, Eric.
Thank you. Okay, thank you. Hopefully you can hear me. Let me adjust this. Yeah, so thank you so much for having me. It's a real pleasure to be here in Bangalore. So over the next few days, I'm going to kind of give an overview of multi-agent reinforced learning, where the field is, kind of some theoretical foundations, some algorithms, and some future directions. Please feel free to interrupt with questions. These things are always more fun when they're more interactive. And I'm going to start with kind of a motivation, which we're all relatively familiar with, which is why we're here, which is that reinforcement learning has really been the driver behind most of AI's successes in recent years, right? So we're all familiar in some sense with AlphaGo, but also DeepMind and StarCraft. That was another great success. More recently, AI has started to beat the best human players in poker tournaments. I think Gaurav mentioned this a lot, which was AI starting to beat people playing Dota 2. And of course, much more recently, oops, it's not working. Much more recently, reinforcement learning has had a very important place in the training and fine-tuning of large language models, right? Maybe the most famous example of this was DeepSeek, and increasingly it's being used to train what are known as these AI agents. But if we look under the hood of a lot of these problems, they're all fundamentally multi-agent. They're all some form of a game where our RL agent or our reinforcement learning algorithm is competing not just against a static environment, but really against another player or a person. And so really, if you look under the surface, these are all successes of multi-agent reinforcement learning, right? In Go, the reinforcement learning agent was trained in self-play. It played itself over and over again until it reached a level where it could beat the best human player in Go. In poker, this is kind of obviously a game of imperfect information between people. Increasingly, same with StarCraft. Increasingly, you have self-driving cars trying to make decisions on roads. In Los Angeles, we actually have quite a few of them actually deployed. And that is really a multi-agent environment. The car has to reason strategically about all of the other cars on the road as it navigates. And obviously, as we move on to more robotic applications. So I hope that you can already see that multi-agent reinforcement learning is already been used to great success. But I would say, and I hope to convince you that multi-agent reinforcement learning compared to reinforcement learning is not very well understood yet. We're kind of lacking a set of solid theoretical foundations. And this is why I think it's such an exciting research area to really look at. So we can think a little bit, just to give you an example, we can think a little bit about what might constitute a very good multi-agent reinforcement learning algorithm. We're all very familiar with AlphaGo, which was this extremely successful algorithm that can beat the best human players when playing Go. This was in 2016, right? DeepMind's AlphaGo beat the human champion 4-1 in a series of games. So it's clearly very good at beating very, very good players. But more recently, there was some work coming out of a team from Berkeley and MIT that shows that you could actually hand design very specific policies to consistently beat AlphaGo in games. So, researchers show that you could basically create policies that could be used by amateurs. So very easy to understand policies that could consistently beat the best, at this point, the best Go playing bot that there was. And the strategy is quite interesting if you look at it. This is just an example of a game. Spoiler alert, I don't really play Go. But from what I understand, white here is being controlled by the human who's trying to manipulate the Go playing bot who plays black. And the really simple strategy used by the person to beat this bot is really just to distract them over here while slowly encircling them on the larger periphery. And so this is a very simple strategy that most human players would immediately see happening, but that this Go playing bot just completely missed. And this tells us a little bit that these Go playing bots are very good at playing very good players, but the strategies that they've learned aren't very robust, and they're not particularly robust in a game theoretic way. Furthermore, there's huge problems of efficiency in multi-agent reinforcement learning. AlphaGo is kind of famous, was trained on something like 10 to the 7 games of Go over a month of training time on dedicated servers. Yep. Yeah, so this was done, they actually handcrafted these. So this was learned not even using reinforcement learning algorithms. This was, they actually just studied the algorithm and created these strategies by inspection almost, which is almost more impressive. And I should say that in this paper, if you read it, the humans that played these Go playing bots had little to no experience playing Go. They were not experienced Go players, but they just went and deployed these strategies because they were adversarial policies basically that they had discovered. Yep. So Go is a 2-player game. And so as we'll see, this is fundamentally what happened is they had 2 separate versions of Go, of AlphaGo, play against each other over and over again. And then the winner would kind of pass on. And then they would play that winner against itself again, 2 versions of that winner. And then they would basically do these evolutionary strategies. And that's a form of self-play, but that's a form of multi-agent reinforcement learning. As we'll see, multi-agent reinforcement learning is just any reinforcement learning problem where there's multiple agents interacting in the same environment.
They could be cooperative or...
They could be cooperative, they could be adversarial, they could be just misaligned. We'll get to the full definition in a little bit. Great. Similarly, just to go back to this point about efficiency being very important, when DeepMind was training Alpha Star, the algorithm that they actually used played something like 200 years of real-time StarCraft games, and again was trained on more than a month of training time on dedicated servers. Both of these are kind of problematic because if we want to take our multi-agent reinforcement learning algorithms and use them in real-world systems for self-driving, or we want to really do something like AI multi-agents, as all of these AI companies are talking about, or actually use them for energy management, our algorithms need to be efficient and they need to be robust. And so far, because we don't have a very good understanding of how to design multi-agent reinforcement learning algorithms, we don't have those 2 properties. And so, the overarching question over the next couple days will really be about whether or not we can establish a principled foundation for multi-agent reinforcement learning. We're going to look into what makes these problems so hard. We're going to try and understand the simple algorithmic foundations that we can build on. And then we're going to study the fundamental limits and the types of algorithms that we can design to achieve them. So to give you an idea of why multi-agent reinforcement learning is so much more complex than single-agent reinforcement learning or just classical reinforcement learning, I like to go back to these very toy pictures. In some sense, this is a toy picture of just a normal machine learning problem, where we have a decision-making algorithm taking in data and making decisions in a static or overall stationary environment. If we make the environment dynamic and uncertain, that gives you reinforcement learning, right? So now you have an uncertain dynamic environment that might be evolving over time, and you want to design an algorithm that can take in data and make decisions in these environments. But multi-agent reinforcement learning really deals with these much more complex environments here, where you have decision-making algorithms making decisions in uncertain dynamic environments that are evolving over time. And these algorithms are interacting not just with other algorithms, but also with people. And multi-agent reinforcement learning really tries to make sense of this entire picture here. The real struggle behind multi-agent reinforcement learning is the fact that this necessitates some form of a strategic interaction. As soon as you have multiple stakeholders in an environment who have potentially misaligned objectives, that gives rise to strategic interactions. And as we'll see, strategic interactions will vastly complicate the task of learning. Just as an example, we don't even know what we should even learn. What's a good objective in a multi-agent reinforcement learning environment? It's unclear. But nevertheless, I think that there's really kind of exciting opportunities here for algorithm design in a way that there aren't in a lot of more mature machine learning fields. So if you really want to try and understand how to design good multi-agent reinforcement learning algorithms, we're going to have to basically draw on 3 different fields of knowledge almost. The first is really algorithms and computation. These are really just tools that are going to be used to design scalable and kind of powerful algorithms, and for us to understand the computational complexity of a lot of the tasks that we care about. We're going to have to necessarily draw on ideas from economics to deal with strategic interactions, really ideas from game theory to deal with these problems. And then lastly, we'll obviously need ideas from control and statistics and optimization, because at the end of the day, these are dynamic problems. We need all 3 of them. We need to go a little bit further than where the field has been in the past. Computer science and economics has a long history of interaction, and that's kind of given rise to this field known as algorithmic game theory. But as we'll see, multi-agent reinforcement learning has to go much further to actually bring in ideas from control into this field. Similarly, control and statistics and economics in some sense has had some connections in econometrics, but these have been mostly too static. And then lastly, we have to go much beyond just classic machine learning and AI and bring in ideas from game theory. And so multi-agent reinforcement learning is really going to draw on all 3 of these fields, which is also why I think it's such an interesting and exciting field to pursue. So a little overview of what we're going to see over the next couple days. So as I mentioned, as we'll see, strategic interactions in these multi-agent environments are going to break our intuition on the behavior of learning algorithms, and they'll give you basically brand new challenges for algorithm design. And I'll give you a very high-level view of what I mean by that. In normal reinforcement learning, as we actually just saw before this, reinforcement learning is, it's a structured non-convex optimization problem, right? But the important thing about reinforcement learning is that it is still an optimization problem, and that's kind of crucial. Multi-agent reinforcement learning, on the other hand, as we're going to kind of explore, it's less about optimization and it's more about equilibrium computation. And I put structured here because it's not entirely clear if there is a lot of structure in these problems that we could exploit, but that's what we'll explore over the next few days. As I'll kind of hope to convince you, structured equilibrium computation is actually just fundamentally hard problem in general. In reinforcement learning, the environment is dynamic, but it's stationary. The environment's not changing over time. The dynamics aren't changing over time. In multi-agent reinforcement learning, the problem is much harder because the coupling between agents in the same environment can introduce non-stationarities in learning, which can make these problems very hard to understand. In particular, the non-stationarity in the environment makes proving convergence of algorithms extremely hard. And so we're going to look at ways to get around this. Similarly, in reinforcement learning, the role of function approximation is somewhat clear. Larger, more expressive model classes or function classes have the potential to yield better performance if you can optimize them and have enough data. But as we'll see in multi-agent reinforcement learning, that's not true anymore. Larger, more expressive function classes can yield worse solutions even if you have infinite data and infinite compute. So, again, a lot of our basic intuition from problems that are normally posed as optimization problems fail as soon as we introduce multiple agents into the environment. So, as we'll see, even though multi-agent reinforcement learning is less well understood theoretically, we're going to build on foundations from game theory and reinforcement learning to explore and design new algorithmic principles over the next few days. And the main question that you should kind of keep in mind is, how do we design principal algorithms for multi-agent problems? And over the next 2 days, we're going to focus really on the theoretical foundations. I wanted to give a quick disclaimer that in some sense, this talk will not be an exhaustive overview of multi-agent reinforcement learning. That's just not possible. We're going to focus mainly on theoretical results. And I hope to just pass on intuition for why these problems are difficult and what principles are used generally to design algorithms for these problems, and maybe hint at potential new research directions. And to that end, I've kind of selected a set of results that I hope make that point. But that's hardly exhaustive. And if someone else was to give that talk, they might focus on a different angle of multi-agent reinforcement learning. But just to give you a disclaimer. Great. So to actually start diving into some of the math, the underlying object in multi-agent reinforcement learning is what's known as a Markov game. Now we saw in the last talk this notion of a Markov decision process, and a Markov game is just a generalization of a Markov decision process to handle multiple agents, and it was introduced by Shapley in 1953. So this is an environment in which there's n different agents. Each agent has their own action space. The agents also have a joint state space. They have a set of dynamics that depend on the current state and the joint action of all of the players. Each of the players is going to have their own reward function. We're not necessarily going to assume that they're related. They could all be completely different. And there's also going to be a horizon. It's either going to be finite or infinite. And there's going to be an initial state distribution, right? And I'm showing on the bottom here just a really simple example of a two-player Markov game. This is an environment in which the environment transitions to a new state st+1 given two actions from two different players, and then it feeds them both two rewards, each their own reward. So this is a pretty general setup. As you can see, it can already encompass single agent Markov decision processes. We just only have one action set. So just to give you an example, if we look at chess or we look at Go, right, the action spaces for each player are just going to be the set of available actions for each player in Go, or the set of available actions on the chessboard. The state space might be the chessboard itself. The dynamics might be just how the chessboard transitions given an action of a player. The rewards are as given. It could be win or lose at the end of the game. And the horizon is finite or infinite, and so on. So as you can see, this is a pretty expressive class of problems, and we'll get to how expressive in a second. But any questions about that setup? Exactly, yeah. So these are just two different multi-agent reinforcement learning algorithms. Yep.
I have a high-level question.
Yep.
In some sense, human beings are also multiple agents who are working together.
Sorry?
Human beings are also, and sometimes organizations work successfully, sometimes. So will there be insights you'll take from how humans work well to this and vice versa?
That's a very good question. So at the end of the 2 days, I'll give you an overview of some more kind of current research, which is exactly this, bringing ideas from behavioral economics and embedding it into multi-agent reinforcement learning. In general, what we'll see is that we'll kind of get a handle on the types of games that people can solve and that algorithms converge on. And as we'll see, those tend to either be cooperative or adversarial. And something in between is where things get hard. Any other questions? Yep.
The next, no, the previous slide where you mentioned all of the different scenarios and you have 3 pictures here. This, yeah, this.
Yeah.
Yeah, this slide. So like in one of the previous slides, you say when your environment is non-stationary, sometimes due to strategic interactions, we might not even know what we are trying to learn.
Mhm.
So can you give me some sort of example? Because like when I think of RL is like, okay, there's some specific problem that I want to solve. And let's say RL would be my framework to go to.
Yeah.
So like, what would the case be when, like, for example?
So I'll get there in 2 slides or 2 or 3 slides. So if I don't answer that question, ask it again. Great. So yeah, just to give you an idea of the interaction protocol or how these games progress. Initially, the environment is going to sample initial state from the initial state distribution. And then for all times afterwards, each agent is going to play an action simultaneously into the environment. I'm going to let AT here just denote the joint action of all the players at time t. Agents are going to receive their immediate reward according to their reward function. And then the environment is going to transition to the next state, right? Given the dynamics. So this is a kind of very simple setting. Importantly, we're going to only look at over the next 2 days these simultaneous play environments. This is still broad enough to capture turn-based games. You just constrain the available actions available to each player. But this is an important distinction to make because in game theory, the order of play can sometimes make a big difference. Great. So that's our interaction protocol. And in this overview, we're going to mainly focus on fully observable tabular Markov games. So we're going to look at situations in which all of the agents observe the joint actions and states that were used at each time. And we're going to look at tabular Markov games, which are games with finite state and action spaces. So finite but large, right? And later on, we'll see how to bring in function approximation to deal with these large state spaces. Great. So now we have to ask, what are the set of strategies available to each player? And so we're going to assume that players optimize over the space of policies. But again, we have to be a little bit careful about how we define this. So we're going to have 3 different classes of strategies available to each player. The first is a general policy, which depends on the entire history of play. In this case, their strategy at the next time is going to be a distribution over actions, which can depend on the entire sequence of play in all of the past steps. Similarly, there's non-stationary Markov policies. These depend only on the current state and time. So in this case, the policy that you're going to implement will only be a function of the current state and the time at which you implement it. These will show up a lot in finite horizon Markov games. And then lastly, we look at stationary Markov policies. These are classes of policies that depend only on the current state and not on time. And so these are going to be the 3 classes of strategy spaces that we're going to allow our players to optimize over. And they're expressive enough to get the point across. Great. So now to evaluate the quality of their strategies, we're going to assume that players seek to maximize their cumulative reward. So we're going to look again at two different scenarios. The first is going to be finite horizon Markov games. In this case, they want to maximize their cumulative reward over a finite time horizon h. And the utility of agent I here is going to depend on the policy of agent I and the policy of all of the other agents. So we're just going to denote this like this. This is going to be our notation. Pi I is going to be the policy of agent I. Pi minus I is going to be the policy of all of the joint policy of all of the other agents except for agent I. And so as you can see, they're coupled through the dynamics here, right? This expectation is taken with respect to the joint policy, the dynamics, and the initial state distribution. So this is the first objective that we might have. And then the second is going to be an infinite horizon problem. In this case, we're going to introduce a discount factor to make sure things stay finite. And now the utility is a discounted cumulative reward, where each player is going to be assumed to have their own discount factor. You could just have a gamma I here. And so these are going to be our 2 objectives for the players. And so just to recap, you have our classic Markov game with maybe an infinite horizon objective here. So as you can see, this subsumes single agent reinforcement learning, quite obviously. We just only have one agent. Another kind of special case that we're going to focus on quite a lot over the next couple of days are going to be two-player zero-sum games. These are going to be games where the reward of one player is going to be the negative of the reward of the other, right? And those are, you could think of as just fully adversarial games, games in which anytime one player's reward goes up, the other one's goes down. And you can think of those as purely competitive games. And then the last will be cooperative. These are when all players are optimizing the same reward function. And then the general class, sometimes I'll call it a general sum game, is when you don't make any of these simplifying assumptions. But importantly, this not only generalizes these very simple or these reinforcement learning problems, they also generalize some important classes of problems from game theory. In particular, they generalize normal form games or repeated normal form games. Those are just games, those are just Markov games where there's no state or a single state and no state transitions. So for example, repeated prisoner's dilemma or even rock, paper, scissors falls into this scenario. There's no sense of state in rock, paper, scissors. We just play our actions over and over again, and we're trying to maximize our win rate essentially. And they also kind of will encompass extensive form games, which are these tree-based games here, which are particularly useful for modeling things like poker. Great. Any questions about that? So now we get to kind of the crux of that question, which are what are good outcomes that we should hope for in Markov games, right? As we kind of saw in Gaurav's talk before, in a single agent reinforcement learning problem, the goal is to maximize your reward. So what you'd actually like to do is find the policy over your action space that maximizes your utility or maximizes your cumulative reward. In games, that might not be possible anymore, right? If each player would like to maximize their own utility, that might not be possible because their objectives are not aligned. So for example, in zero-sum games, if I increase my utility, it decreases the utility of someone else in the game. Players can't all jointly maximize their utility function. So maybe something that we might want is that we might want to find a policy that best exploits my opponent's current policy. So maybe we'd like to play what's known as a best response to my opponent's policy pi minus I. That might be the argmax given pi minus I is fixed. That might seem like a good strategy. That is, for example, what was done in AlphaGo. You come up with the best policy against the human expert, right? Pi minus I might be the best human player of Go, and you want to find a policy that can consistently defeat them. But that might not be a very robust strategy because it's only good against a fixed strategy, but it might not be a good strategy if my opponents adapt, right? And so a good outcome in games should be an equilibrium. No player should be able to deviate from their strategy under kind of a set of rational deviations, right? And as soon as you hear those words, that should immediately make you think of a Nash equilibrium, right? And so a good outcome for a Markov game is normally considered to be a Nash equilibrium in their space of policies. And a Nash equilibrium is going to be a set of a joint policy where no player has any incentive to unilaterally deviate to increase their reward, right? So given that my opponents are fixed, no other policy can increase my reward. Any questions about that definition of Nash? If you've never seen it, it could be a little bit, hard to understand. Great. So at Nash, each player is at a best response to their opponent's current policy. So they, by definition, have no incentive to unilaterally deviate. And as we'll see, Nash is always guaranteed to exist in Markov policies in Markov games. So a Nash is guaranteed to exist in non-stationary Markov policies for finite horizon games. And it's guaranteed to exist in the space of stationary Markov policies for infinite horizon games. So that's, at least we know this equilibrium notion exists. And so hopefully we should be able to actually compute it. If we were to specialize to zero-sum games, the Nash equilibrium is the same thing as the min-max solution. So that's just the Nash equilibrium would just be equal to the min-max and the max-min of the problem. If you're from an optimization background, this might look very familiar to you. This is nothing but saying strong duality holds. But this is not due to von Neumann's minimax theorem. It was actually proved by Shapley via dynamic programming because these objective functions are not convex in general. So, I hope to have convinced you so far that a Nash equilibrium is maybe the best outcome that we could hope for in a game. Any questions?
Sorry, so what assumptions does Shapley make on you?
Basically just a bounded reward. Yeah. That's all you need. Like bounded reward, finite state, finite action, and then you'll have this property here.
And that's a very special two-player setting result.
This is specific to zero-sum games. Yeah. Beyond zero-sum games, this won't be true. Yep.
You are studying the Nash equilibrium because that's the best joint optimal play.
Yeah, so a Nash equilibrium isn't going to be the best joint optimal strategy, but it's basically a fixed point. And that's the best that you could hope for in these kind of game theoretic scenarios. You shouldn't be able to hope for any kind of joint optimization or problem to hold.
I get this, but my question is, there could be Nash equilibriums, but unless you could, as an agent, you could take the whole game towards the Nash equilibrium.
Mm-hmm.
Unless you can do that, the Nash itself is not interesting.
Yeah, exactly. So you're asking a good question, which is that we should hope for the Nash to be the outcome of learning in some sense here. We should hope to converge to a Nash equilibrium if players use kind of rational learning algorithms. So you're right in a sense that a Nash, we shouldn't hope for players to just play Nash immediately. But if they're using some form of a learning algorithm, we should hope for them to converge to a Nash. Because in some sense, it's a rational fixed point for them to actually converge to. Oh, sorry, I think there was a question there first. In what sense? So here, what rational means is it just means that you're at a best response to your opponent's strategy. So if you weren't rational in a zero-sum game, you wouldn't be playing a min, given the other players playing a max. So you wouldn't be at this Nash equilibrium strategy, right? So rational just means that you're going to deviate only to strategies that increase your reward, right? Yep. Oh, sorry. There was a question here first, then we'll come back. Yeah, that's a very good question. So right now we haven't talked at all. Nash equilibria, there might be multiple Nash equilibria in a game. In zero-sum games, the magic is that all Nash have to basically equal this min-max value. So different Nash won't yield you better results. In general-sum games, that's not true anymore. You have an equilibrium selection problem, which is non-trivial. You might have one Nash that you prefer because you have a higher reward, and another Nash that you dislike because you have a lower reward. But at the moment, we're not going to get into those details. Mm-hmm.
As in, because you could backtrack in non-stationary games. So maybe the Nash that you've gotten is not the best outcome. Like there's another Nash that you should prefer.
Yeah, exactly. So that's where we haven't talked about equilibrium selection yet, but it's something that will come up and is also very important because you're exactly right. You might prefer one Nash to another. All I'm saying here is that the outcome that we should expect for a learning algorithm in a multi-agent reinforced learning problem is basically a Nash because these are the set of fixed points that make sense for rational algorithms, right? But we still have to see, how do we get to better Nash or worse Nash or anything like that. These, I would not conflate them with local minima too much because these are still global in a sense where you have no incentive to globally deviate given anyone is fixed. But you can, I mean, you're not totally off because, there's different Nash that might be better solutions. So if you think of the joint landscape, there might be one Nash that Pareto dominates all the other Nash. But yeah, we're really not at that point yet. But these are really good questions because you're really thinking about, the nuances of this definition.
So in Shapleigh's theorem, so what is the assumption? Like the set of actions is finite, or?
Yeah, finite states, finite actions, and bounded reward, I think.
All right.
And then maybe a discount, and then in the infinite horizon, a discount factor less than 1. Basically, the proof is you basically show for the infinite horizon problem, you show there's a contraction mapping.
So for example, if the set of actions is not finite, then you might have to resort to some assumption on something like that von Neumann's min-max theorem or something.
Yeah. Von Neumann's min-max theorem won't hold because that requires kind of convexity and concavity. But if you go to like an infinite state or an infinite action space, most of the time you could resort to other, like there are other min-max theorems. You could resort to like a
You cannot do with a non-convex. Okay,
yeah.
Okay, all right.
There's a lot of min-max theorems that you could basically choose, and you would basically get some similar result. Great. So we focused a lot on Nash, which is good, but unfortunately computing a Nash equilibrium is hard, even in simple 2-player normal form games. And what I mean by that is there was kind of this seminal paper by Kostas Stathakis and Christos Papadimitriou in 2009, which basically said that computing a Nash equilibrium of even a 2-player normal form game is in PPAD, which is a class of problems that are generally considered to be intractable. Think of them as being like NP hard, but these are classes of hard problems where we could verify in polynomial time. But the kind of canonical example you should keep in mind is computing a Brouwer fixed point. But the takeaway is just that these are just a hard class of problems in general. Even if I have full information on the game, and I control all the players, and I want to in a centralized way compute a Nash, that's in general an intractable problem, right? And so maybe a question that we're going to return to over and over again over the next couple of days is, are there other equilibrium concepts that are more amenable to learning? Great, and that kind of gets me to the roadmap of what we're going to look at for the next couple of days. So we're going to, for the next part of the beginning of this talk, we're going to focus on normal form and concave games. And we're really going to dive deep into this problem of equilibrium computation and learning in games, right? So these are going to be very simple games in which it's just kind of a repeated matrix game. We're not going to assume any dynamics or any of the kind of complicated structure of a multi-agent reinforcement learning problem. And we're going to look at what are the types of equilibria that we can compute. And what are the set of learning algorithms that people have developed, right? And this is really going to draw on ideas from economics and the long history of understanding learning in games and in economics. Later on, we're going to kind of move on to multi-agent reinforcement learning. We'll look at policy gradient algorithms in games, the types of guarantees that those algorithms might have. We'll move on to value-based algorithms, and we'll think a little bit about the role of function approximation. And then in the last hour tomorrow, we're going to look at future directions. So maybe we'll think about how we can design algorithms for with function approximation for zero-sum games, and maybe even newer equilibrium concepts that have kind of stronger properties in Markov games. Great. So we'll dive right into this first part of the talk, and we're going to look at normal form games. And so we're going to and concave games. And so a normal form game is just a very simple setting in which there's no state, and players would like to maximize their expected reward. And their expected reward is just the expectation of this reward given the joint policy of all of the players. So there's no dynamics here. Players are just optimizing over the simplex. Right? So the policy space is just simplified to a cardinality of a dimensional simplex, kind of the simplest setting. This is the setting that was studied by Nash. And in 1950, he said Nash equilibria always exist in mixed strategies in normal form games. So a Nash equilibrium is always guaranteed to exist for this problem, right? So in two-player games, this simplifies to a very simple matrix game, which we could write as this structure here, where the objective of one player is just this kind of bilinear form here, right? So where players would like to maximize their objective function, so maximize this kind of bilinear form, where R is just the reward matrix for player I. Great. So we could immediately generalize this class of games to a more general class of concave games, where the utility is concave in your own policy for all fixed policy of your opponents, right? And in some sense, you could immediately see that that's true here because this is linear, so it's necessarily concave in your own policy, given that everyone else is fixed. And so this is, just a very simple generalization of that problem. And again, there's another kind of fixed point theorem from Rosen in 1965 that said that Nash equilibria will always exist in concave games over compact and convex strategy spaces, right? Great. So we're going to now assume that we're in a full information regime. Players know their utility, they observe their opponent's full policy, and they seek to adapt online to their opponent's strategies. And so this is going to be the interaction protocol that we're going to analyze for the next little bit. Each agent is going to choose an initial action or initial policy pi I. At each step, they're going to play a policy simultaneously into the environment. They're going to receive their immediate utility and observe their opponent's policy pi minus I. And then they're going to update their policy given their observation, right? So where this is a very kind of simple interaction protocol. Again, players are playing simultaneously, and they're just going to kind of keep doing this ad infinitum, right? And we can start thinking a little bit about what good algorithms look like for these problems, right? What might we want out of a simple learning algorithm for this type of problem? Maybe we'd like, if my opponent's policy doesn't move, I'd like to start exploiting them. I'd like to converge to my best response, right? So maybe a best response type of dynamics works, right? So the simplest class of algorithms that were studied in the literature on learning in games and economics going back 60, 70 years were algorithms that rely on these best response oracles, which basically just assume that I could compute this argmax here, right? So given my opponent's fixed policy pi minus I could just compute my best response. And so the simplest, most naive algorithm that I might converge to is every player is just going to use the best response dynamics, right? At each step, every player is going to choose an initial action, and then afterwards, they're always going to best respond to the last action that they saw. Sorry? So here they're all optimizing simultaneously. Right, but your intuition is right in the sense that this algorithm clearly won't converge, right? In the sense this algorithm is it's almost made to converge to cycles, right? And the simplest example of this is just think of doing this in rock, paper, scissors, right? If you play rock, then I'll immediately play paper on the next round, and we'll just end up cycling for all time. So this is clearly not a good algorithm. It's too greedy. So it doesn't even converge to Nash, even in a very simple game, zero-sum game like rock, paper, scissors. So maybe another algorithm that we might try is what's known as fictitious play, which is maybe a little bit less greedy. It says that I'm going to best respond to my opponent's empirical history of play. So each agent is going to initialize a belief over their opponent's strategy, pi hat minus I. And then for each time, they're going to basically play according to the best response to pi hat. They're going to observe their opponent's strategy and then update their belief, right? So this is a very simple algorithm. Again, in rock, paper, scissors, this makes a lot of sense, right? I'm going to look at how many times you've played rock, how many times you've played scissors, and how many times you've played paper in the past. And I'm going to best response because it seems like you're favoring rock over paper, right? So again, a very kind of classic algorithm. It was first analyzed by Brown in 1949. Players best respond to their opponent's empirical history of play. And so kind of there's a kind of classic result. Robinson in 1951 showed that fictitious play will asymptotically converge to Nash in zero-sum games. So in his proof, he actually had a rate of convergence. He said it converged at a 1 over epsilon to the number of actions, number of iterations, to an epsilon approximate Nash equilibrium. So that was kind of a nice result. 1959, Carlin actually conjectured that this should actually just be O to the 1 over epsilon squared across all games. And then this was actually refuted more recently by Daskalakis and Penn, which showed that this rate was kind of the correct rate in the worst case for fictitious play. So there's been a lot of kind of analysis of this algorithm in zero-sum games, but fictitious play has no convergence guarantees in more general games. Beyond zero-sum and beyond kind of purely cooperative games, fictitious play won't converge to anything meaningful. So if we kind of go back to the drawing board a little bit, we could think a little bit about what we might actually want for when we design algorithms for learning in games, right? If we saw best response dynamics and we saw fictitious play, both of those were actually nice because agents, it was just an independent algorithm. Agents could implement their algorithm without knowing anything about their opponent's utility. Both of those algorithms were what are known as individually rationalizable. Agents could take advantage of naive opponents, right? If my opponent was fixed, I would converge to the best response, which is the best thing I can do. Unfortunately, they weren't convergent to Nash, right? We've actually, and in particular, we should kind of believe that this is too much to ever hope for a learning algorithm, because otherwise, it would get around that kind of computational hardness of that problem. And actually, there's even some more classic work in economics that said that uncoupled and independent dynamics, cannot always converge to Nash. It's impossible to come up with a set of dynamics that consistently converge to Nash across all games. So, that kind of led the field of learning in games to focus on a different desiderata. Instead of converging to Nash, they asked that the algorithm be no regret, which is that the algorithm should compete with the best fixed action in hindsight, right? So this, again, might make sense. We're going to play the game over and over again. And then at the end, at time capital T, I'm going to look into the past and I'm going to say, I did as well as if I had just, fixed my action to the best fixed action that I could have done the entire time, right? And this is a very kind of simple notion, and it's very popular in online learning, as you'll see kind of, I think, later on over the course of the week. And this is, obviously a weakening, right? This doesn't guarantee that you converge to Nash at all. Any questions about? Yep. Oh, small O of 1 means that it's just going to decay. Like this quantity decays in capital T. As you take the limit as T goes to infinity, this will decay to 0. Sorry? Yeah, and this is true for all A. Yeah, exactly. Great. So this is the notion of kind of a no regret algorithm. Again, it was very popular in learning in games. And more recently, it's been extremely popular in what are known as adversarial bandit problems. And many well-known algorithms can actually be shown to be no regret. Online gradient play, multiplicative weights, mirror descent, smooth version of fictitious play are all satisfy this property here. But fictitious play and best response dynamics, importantly, are not no regret algorithms. Yep.
So in a lot of games that we play in real life, people do care about my difference with the opponent's utility.
Mm-hmm.
But if the agents do not know about each other's utility, how do we incorporate that in the game? Like, I care about fairness. Like, even if my payoff is 0, I would want your payoff to be somewhat.
Yeah, that's a good question. Here, we're not considering agents that care about the other agents at all. They're completely self-interested. Yeah, but that's a good. I mean, on like bringing in those types of constraints, there are obviously very important twists on all these problems.
Thank you.
Yep. Sorry.
perhaps take the difference of the original.
Yeah. Yeah, that's true. In that case, you could take the difference of the two players' utilities and just take that as the player's utility, right? And then optimize this. But then obviously that would break this independent learning assumption. But that's fine because you're basically saying that you don't want independent learning in that setting.
Can one practically justify this no regret algorithms? Is there a real world setting where it makes sense where people actually kind of behave like this?
Yeah, so actually there's been there's actually quite a few works in behavioral economics showing that this is not a terrible approximation of what people might do. Not because people kind of reason in this post hoc way, but just that these algorithms are actually, they kind of force you to hedge a little bit, and you can't be too greedy, and it ends up being kind of what people do in practice. And we'll actually motivate on the next slide from a game theoretic standpoint as well.
Okay.
So as we'll see, using
I want to say one question.
Yep.
Kind of stupid, but so here this pi minus IT also depends generally on pi IT, right?
on psi IT, yeah.
Because other agents are also changing their thing.
Yeah.
So isn't this a bit like too greedy? You're assuming that everybody else is fixed, and then you're changing your policy.
Yeah, so this is what you'd like your pi IT to compete against. You'd like it to compete against the best, the max of the kind of average utility that you've seen across the history of play. You are completely if you have a strategy that satisfies this, it's completely correlated with the other player's strategy. Yeah, but it's not correlated. It's correlated through the sequence of play, but not like algorithmically, not by optimizing their utility.
Yeah, I guess what I'm saying is that if I actually played pi prime,
Yeah.
others would not have played pi.
Yeah, exactly. So it's only true. It's not true in this kind of counterfactual way, right? It's true just in a post hoc way. Yeah,
Thanks.
yeah, that's a good point.
Can you please repeat the intuition behind the no regret? I didn't quite fully get that.
Yeah, so basically the idea why you might want this is because you might want to, at the end of, let's say you play for a horizon capital T, you look at what you did in the past and you said, and you might want to, have done as well as the best fixed action that you could do, right? That's all that no regret is saying. There are strengthenings of this no regret idea, but this is the simplest. Yep.
So when defining the Nash equilibrium, do you define it for each time step? You look at the best response, or you look at the vector for each t you have pi t, so and pi it, and do you define the Nash equilibrium for the whole?
Yeah, so here this isn't a Nash. As we'll see, it's actually a completely different solution concept, because here this is a max over the sum, right? So it's not for every time, if that makes sense, if that answers your question.
So my question was about the definition of Nash equilibrium.
Oh yeah, for a definition of Nash, then it's just you're just saying that you want, given that your opponents are at the Nash equilibrium, you want to have no incentive to deviate. So you should be at a max for yourself.
Yeah. So so the policy is defined for a single time, or it's a sequence of policies for all time?
So a Nash is just a fixed policy, but it's if you were at Nash, then you would have obviously no incentive to deviate, right? So it would end up being the same fixed policy that you would play for all time.
Okay.
Yeah. Yep.
So when we say many well-known algorithms turn out to be no regret, so take any algorithm, say multiplicative weights. Are we assuming all the players are playing multiplicative weights, or only one player is playing multiplicative weights, and irrespective of whatever these other players play, I'll be in no regret?
Yeah, that's a very good question. So the magic actually of no regret algorithms is this is true. You can actually show that this is true for arbitrary plays of the other player. So all of these algorithms don't at all rely on the fact that your opponent is using a no regret algorithm. All it's saying is that I can guarantee that this is true for any sequence of pi minus IT, right? And that's actually a very powerful property, right?
So this includes if the opponent is adversarial in nature as well.
Yep. They could be completely adversarial to you, but a no regret algorithm will basically guarantee that this is true. which is remarkable if you think about it. It takes a little bit to get your head around it, because it says that you could compete against arbitrary adversarial loss sequences.
Can you do better if you know your adversaries, if your opponents are following this no regret algorithm?
That's a very good question too. So that's actually a kind of emerging research area where people are looking at the metagame now. We're saying like if everyone's using a no regret algorithm, as we'll see on the next slide, it gives us a certain outcome. But if you could deviate from it, and actually you can most of the time dominate a no regret algorithm quite easily. Great. No, great questions. So as we'll see, no regret algorithms have convergence guarantees to another form of game theoretic equilibrium, not a Nash equilibrium. And that notion is what's known as a coarse correlated equilibrium. This is a notion that was put forward by Aumann in 1974. So a joint distribution, sigma, is going to be a coarse correlated equilibrium. So this is a joint distribution over the joint action space of all of the players. Is going to be a coarse correlated equilibrium if for all I, all players obeying this joint strategy sigma have no incentive to unilaterally deviate, given that everyone else's strategy is drawn according to sigma. So this looks a lot like the definition of a Nash equilibrium, right? The main difference is that sigma is a joint strategy, so it can correlate all of the players, right? A Nash equilibrium is basically a coarse correlated equilibrium where this sigma is a product distribution, right? So it decomposes across all of the players' action spaces, right? And so as I'll show you in the next little bit, when every player is using a no regret algorithm, they're going to converge to a coarse correlated equilibrium of the game, right? So that's a very kind of strong, powerful property, right? And so the proof of this is almost by definition. So let's look at the sequence of correlated joint strategies. But let's just make it, and let's define sigma t to just be the uniform across all of the history of play, right? So with probability 1 over t, I draw the strategy that was played at time t, the joint strategy played at time t. From the no regret property of the algorithm that everyone used, for all players, I'm guaranteed that this is true. So the max under this distribution has to satisfy this set of thinking here. This is just the definition of a no regret algorithm. If I take limits as t goes to infinity, then I'm guaranteed that this is true, which is the definition of a coarse correlated equilibrium, right? And so what this says is that the joint history of play, when players use no regret learning algorithms, converges to a coarse correlated equilibrium. And that's very powerful, right? Because we saw that this wasn't possible for Nash equilibria in general. It would be impossible to come up with an algorithm to compute a Nash equilibrium in general. But in all of these normal form games, using no regret learning, we could compute a coarse correlated equilibrium of the game, right? And that's kind of this very nice property. Most of these no regret algorithms converge at a polynomial rate, right? And so this basically says that we could approximate a coarse correlated equilibrium in polynomial time. Any questions about that result? This is kind of one of the most foundational results in game theory or learning in games. Great. So CCE have several desirable properties. They always exist, right? It's just a generalization of a Nash equilibrium. So if a Nash equilibrium exists, a CCE exists. The set of CCE is always convex. Actually, the CCE can be found in normal form games via either linear programming, if in a centralized way, or no regret learning in a decentralized way. Every player is just going to run a no regret learning algorithm. But they also have some less desirable properties. There is some kind of interesting work in 2013 that basically showed that CCE can have support on dominated strategies. So no rational agent would implement this CCE, right? Because a dominated strategy is a strategy where there's always one action that is better for you to use. But for some reason, you could actually come up with a situation in which a CCE puts positive weight on that strategy, which is kind of interesting. As we'll see, you can deploy a no regret algorithm and you might never actually converge in an iterate sense, right? So this is saying something about the joint, our previous results is something about the joint strategies It doesn't say anything about the iterates that were actually used or the strategies that were actually, the actual strategies that were used. And we'll see on the next slide what's happening. And the last kind of downside to a CCC is that, in some sense, it requires coordination to implement, right? Because I have to use a joint strategy, right? Sorry, a joint distribution here. Great.
Can you go over that can be no regret but never converge again?
Yep, I'll give you an example on the next slide. So just to give you an example of this, let's look at the dynamics of no regret algorithms and kind of the simplest game possible. So we're going to look at a 2-player game. This is going to be rock, paper, scissors. Think of each entry. This is going to be rock, paper, scissors, rock, paper, scissors. If we play the same action, it's a tie. Otherwise it just has this reward structure here. And we're going to assume that players optimize over softmax policies using gradient descent. So they have basically a set of weights associated to each action, and they're just going to do gradient ascent on their loss given their opponent's last strategy. This is a no regret learning algorithm, right? And then they're just going to take their policy that they use is going to be a softmax over the weights. So this is a no regret learning algorithm. And if we were to actually use it to play rock, paper, scissors, this is the type of behavior that would emerge. Yep. Yeah, so there's kind of a general proof structure to those proofs. You kind of just analyze, you could start by just analyzing basically it's almost like the convergence of gradient descent on a convex function. And what you can actually show is that that analysis will work for any sequence of convex functions, and that basically gives you your result. So gradient descent on any convex function has some form of convergence, and that kind of just extends. Yep.
Is that the payoff are not needed? Other players do not know the payoff of other.
Yeah.
They're not coupled.
Yeah, so in this sense, they're not coupled. The only reason they're coupled is because it's a symmetric game. Yeah. And so this is the behavior that you get out of playing this no regret algorithm in this game. And so what I'm doing here is I'm just kind of projecting the 2 x's are the weight on paper, the weight on rock for one of the players, and the weight on scissors for the third player. So I'm just projecting from the 6-dimensional space down to the 3-dimensional space. The circle is basically showing you the current strategy that was played at that iteration by the players. And what you'll see is that the players are never actually converging. They're tracing out the surface of this torus for all time in this 3-dimensional space. They will actually never repeat themselves. So it's actually not a cycle. And actually in a dynamical system sense, it's a form of chaos because it's a very kind of controlled form of chaos, but it's technically chaotic dynamics. And so, again, you have this very kind of complicated dynamic that emerges out of these no regret learning algorithms. If you were to average the strategy that was played across this torus, you would see that it's 1/3, 1/3, 1/3, which is the Nash equilibrium of the game, which is why the average history of play is converging to a Nash or a CCE. But the actual iterates themselves are never actually converging, right? They're tracing out the surface of this torus for all time. Great. I'm not sure how much time I have left, so. 12:30? Okay, perfect. That'll finish.
Hi, so you're trying 12:40.
Okay, perfect.
So
we'll finish this part, and then that might be a natural place to end.
Vivek, a quick question for you.
Yep.
Is there kind of idea that, maybe we can perturb the rewards, add some kind of penalties to them, and then come to converge to a solution which is well behaved and, the minimum perturbation, so to speak, to get there?
Yeah, that's a very good question. So there is this idea, there's this whole idea of what's known as a quantor response equilibrium, which you could think of as just a perturbation to the underlying objective function. Think of every player as just regularizing just a little bit. That tends to make these problems of non-convergence disappear. but then obviously you're converging to something else. But you need, unfortunately, most of the time to get convergence from perturbations, you need to perturb enough. So the amount of perturbation is, has to be enough to give you the right.
This is a mathematically well-defined problem. One can say nice things.
Yeah. People have looked at it's so there's a class of equilibria known as quantal response equilibria, which kind of are the equilibria that might come out of perturbations. Yeah. Great. So just to recap what we've seen about no regret learning in games, right? So we've seen in general some games we have this class of CCE. This class of CCE includes Nash equilibria, right? And this class of CCE can be computed via no regret learning, right? Or linear programming. There's another class of what are known as correlated equilibria instead of coarse correlated equilibria. They inherit many of the properties of CCE. They can actually be computed via what are known as no swap regret algorithms. That's a little bit out of the scope of these talks, but I'm happy to discuss it if people are interested. And then you have Nash, which we know are kind of intractable to compute. In zero-sum games, the picture is a lot nicer because what you could show is that there's this phenomenon known as equilibrium collapse. So in Nash equilibria, all CCE all CCE are the set of CCE is the set of Nash equilibria, basically. And so no regret algorithms will always find Nash equilibria in zero-sum games. This is a phenomenon, as I said, that's known as equilibrium collapse. The same phenomenon occurs in other kind of strictly competitive games where if I increase my reward, you lose some of your reward. These kind of happen in things like network zero-sum games and things like this, if you're interested. But that's kind of going to conclude our overview of no regret learning algorithms. It's still a pretty active area of research, I would say. So I've just kind of pulled together a few kind of recent papers on these topics. There's a lot of recent work on kind of coming up with optimal rates of convergence or optimal regret bounds. There's work on trying to understand the subset of CCE that you might converge to if you use no regret learning algorithms. There's obviously work on swap regret and converging to correlated equilibria. And then there's a lot of variations on what happens if the games are time varying, what happens if you just want to explore the game, and so on. So this is a very active research field in itself. But I'm happy to answer questions. But for the purposes of multi-agent reinforcement learning, this is kind of the bare minimum that we need. Cool. Any questions? So another lens that we could take to look at equilibrium computation, which I thought might be useful, is the lens of optimization. And this is I thought this could be a useful thing to look at given the title of this workshop. And so we're going to look at equilibrium computation now from the lens of solving variational inequalities. And so as we'll see, computing and learning in Nash equilibrium, we could actually see is equivalent to solving a variation inequality problem. And so basically what we could see is we could define a Nash equilibrium and kind of using first order information, where a joint policy pi star is a Nash equilibrium for a concave game if it satisfies this condition here for all pi, where F is basically this mapping of the player's individual gradients. So I'm just going to vectorize, I'm going to just take a vector of each player's gradient with respect to their own strategy. I'm just going to put it into this object f of pi here. And I'm going to ask that f of pi at a Nash has to satisfy this condition here. This is a useful perspective to take because if this mapping f has some useful structure, maybe it's a monotone mapping, then we could apply tools from the literature on solving variational inequalities to computing and learning Nash equilibria. Okay. I'm missing a slide here, but just this definition you could see is actually just the generalization of the characterization of the maximum of a concave function, right? If there's only one player, this is basically saying that pi star is the max of a function over the simplex, right? Over a constrained set. Any questions about this? Great, so this is kind of the optimization viewpoint on computing a Nash equilibrium. I could basically pose it as trying to solve find a solution to this variational inequality problem. Maybe the most kind of, yep. So a variational equality problem is just saying I want to find a solution, given I have some mapping F, and I'd like to find a solution that satisfies this for all pi across your set. This is the definition of a variational equality problem. You could think of it as a generalization of an optimization problem to multiple objectives, or to this operator F that might not be the gradient of a function. But if F is the gradient of a function, this is just maximization.
Is there a CCE version of this as well, coarse correlated equilibrium?
That's a good question, actually. Not really, actually. Not that I know of.
Just replace the toric value by.
Yeah, you can, but it's a little bit harder to write because it's a CCE is it's an expectation over the simplex kind of. Yeah, it's yep. Yeah, it's concave here, so you're right. It's because I wanted to keep the notation consistent. So if we were minimizing, you'd be completely right. Yeah. Okay. So kind of one of the most kind of classic algorithms that we might use to actually solve these variational equality problems might be just gradient play. This is, or projected gradient play. This is the case where each player is basically just going to try to perform gradient ascent on their loss, right? If we look at the joint dynamics, that just looks like the joint strategy of all the players is evolving according to these dynamics here. It's just the projected kind of monotone mapping, right? Or you take a step in the direction of the monotone mapping and you project back onto your set. So importantly, what makes this approach so much harder than just normal optimization is that these joint dynamics are not, F here is not necessarily the gradient of a function. It's the gradient of many different functions, right? And that's what makes these problems so hard. Great. So here's, under different conditions on this F, you can give different kind of convergence guarantees. So if F is strongly monotone, then you can actually show that you'll converge to the unique Nash under projected gradient play. And so you basically just get this kind of recursion here. So you'll get actually exponential convergence to Nash. If F is just merely monotone, which means that F satisfies this and this condition here for all pi and pi prime in your set, and if the set of joint policies is convex and compact, then under projected gradient play, you could show that the average iterate will converge to Nash. Yep, like in rock, paper, scissors. And so this on the left is what's known as convergence to Nash in a last iterate sense. The iterates of the game are converging to Nash. On the right, we have ergodic convergence to Nash. So the average iterate is converging. And basically, I should mention that a monotone F is true for all zero-sum normal form games and all convex concave games. So for a lot of min-max optimization problems, you actually do have a monotone F. And so this is kind of there's a big connection here with the literature on min-max optimization. And so I should say a monotone F is just a restriction on concave games. All monotone F are concave. Like any game that gives rise to a monotone F has to be a concave game. Not every concave game is monotone. Great. And so just to give you some idea of why all zero-sum normal form games are monotone, this is the structure of a zero-sum normal form game. F in this case is going to be this A matrix times pi, where A is this anti-symmetric matrix, 0R minus R0, because one player is doing gradient ascent, the other one is doing gradient descent, right? And so you can see that A here is anti-symmetric. And so if we look at this object here, you'll see that this condition here is just uniformly 0 for all pi and pi prime. And so F is monotone in all zero-sum games. Cool. But you could actually do better than this average convergence. And this is where we start really diving into the structure or into the literature on solving these monotone variation inequalities. To see why we can only get average convergence, it's useful to go into continuous time and to look at kind of the local structure of these solutions. If we look at the local structure of a solution, f of pi, we'll see that under the limiting continuous time dynamics, you just kind of have this set of cycles. And so anytime you initialize, you're just going to cycle at a constant distance away from the Nash equilibrium in continuous time. When we kind of move to gradient descent or gradient play, we could think of this as a forward Euler discretization of these limiting continuous time dynamics. And then your discretization error kind of forces you to diverge, right? And so in some sense, you'll never actually have last iterate convergence just using naive gradient play or just using this algorithm here. However, so basically a bad discretization is what's causing divergence. And so the only reason you're getting convergence on average to Nash is because your set of strategies is compact. But however, we could fix this by doing what's known as an implicit discretization. This gives rise to what's known as the proximal point algorithm, right? So you can see it's implicit because pi t plus 1 has to satisfy this implicit definition here, where it's pi t plus f of pi t plus 1. You could think of this as the implicit discretization of this ODE, in which case you would actually get convergence. And that's actually, you could actually prove it. So if f is monotone, the action set is compact and convex, then the proximal point algorithm guarantees convergence in a last iterate sense. And in convex concave zero-sum games, you could actually even back out a rate of convergence. So you get convergence in what's known as this measure known as the Nash gap, which basically is a Lyapunov function. For those of you that know, it kind of captures the distance from a Nash equilibrium of the current policy. Great. However, it's not an implementable algorithm because obviously there's this implicit definition here. And so there are kind of two classes of algorithms that have emerged, especially from this literature. One is what's known as the past extra gradient algorithm, and the other is the optimistic gradient algorithm. Both of them you could think of as just doing an intermediate step, evaluating the mapping at that intermediate step, and then applying it to the original point. You could think of both of these as approximations to the proximal point method. There's actually some really nice work by Mokhtari in 2019 that made that kind of rigorous. But again, both algorithms are examples of independent learning in which players don't need to know anything about their opponent's objective to implement. And what you could actually show is that they also have the same convergence guarantees as the proximal point algorithm in these convex concave games. And this is actually extremely recent work, right? So even though these are pretty old algorithms, this convergence result is from like 2 or 3 years ago. So this is very new. So I should mention, interestingly, the optimistic gradient algorithm is no regret as well. The extra gradient algorithm is not a no regret algorithm. There's a proof of that as well. Yep. This is true even actually if this is just RD, right? So this is just the condition that they looked at in this paper. But this is true over RD as well. And then a monotone mapping arises in convex concave min-max optimization and several other contexts as well. Great. So kind of just to recap, and then we'll maybe leave it there. We've seen kind of equilibrium computation from two lenses. The second has been equilibrium computation as optimization. And we've seen that we could cast the problem of computing a Nash equilibrium as the problem of solving what's known as a variation inequality problem. So in subclasses of games, like zero-sum games, potential games, this viewpoint allows you to use kind of new algorithms with strong guarantees of convergence to actually compute game theoretic equilibria. So for example, these have had a lot of research interest around these two algorithms in particular in recent years. Both of these algorithms are independent learning algorithms, which we might actually want to use for games, and they have last iterate convergence to Nash in monotone variation in monotone games. And again, as I mentioned, this is a very active area of research. So again, here's just a list of recent work on kind of convergence of on these kind of monotone variation inequalities. But that also kind of is a nice place to end. We basically looked at normal form and concave games. And we've looked at equilibrium computation and learning in games. And what we've basically seen is that equilibrium computation, even in normal form games, is a pretty hard task. The coupling between agents gives rise to non-stationarity, and we get kind of complex dynamics out of that. But we've seen kind of no regret learning and variational inequality perspectives could be very useful for designing, for getting convergence to game theoretically meaningful solutions like coarse correlate equilibria. And so we're going to use some of these ideas as building blocks as we move back towards multi-agent reinforcement learning after lunch. But with that, thanks so much.